Hello class, welcome back. Last class we talked about energy levels, sublevels, orbitals, and we even talked about the number of electrons that can be in those energy levels. Now we want to talk about atomic spectroscopy. Each wavelength in the spectrum of an atom corresponds to an electron transition between the quantum mechanical orbitals. That's each wavelength in a spectrum of an atom corresponds to an electron transition between quantum mechanical orbitals. And when an electron is excited, its transition from an orbital in a lower energy level to an orbital in a higher energy level, because it has absorbed energy. So when it absorbs energy, it leads from a lower energy level to a higher energy level. And when an electron relaxes, it transitions from an orbital in a higher energy level to an orbital in a lower energy level, giving out the electron, the energy it absorbs. So when an electron relaxes, a photon of light is released, whose energy equals the energy difference between the orbitals. So that is what is happening. In order to transition to a higher energy state, the electron must gain exact amount of energy corresponding to the difference between the final and the initial state. It must absorb exact amount of energy, exact. The electrons in higher energy state are unstable and tend to lose energy and transition to lower energy states. Each line in the emission spectrum corresponds to the difference in energy between two states. So each of those lines we saw corresponds to the difference in energy between two energy states. So that's it. So look, the atom has absorbed energy from n equals to 1 to n equals to 3. When it gives out the energy, you see, it falls back from n equals to 3 to n equals to 2. It gives out the energy in the form of light. Then it falls back in the lower energy level. So the wavelength of line in the emission spectrum of hydrogen can be predicted by calculating the difference in energy between these two states. So for an electron in energy level n, there are n-1 energy states it can transition to. And therefore, n-1 lines can be generated or produced. Both Bohr and quantum mechanical models can predict these lines very accurately for one electron system. For one electron system. The energy of a photon released is equal to the difference in energy between the two levels the electron is jumping between. So this is it. That change in electron energy is equal to final state minus A initial state. So energy emitted by the photon is just the change in energy of the electron. It's just a change in the energy of the electron. And we can calculate it like this. E photon. You see, this is the E photon. So this is N final, the final energy level, minus N initial. This is a constant. So when you do this equation, you get the E photon. And from the E photon, you can find the wavelength of the energy. So this is E photon. This is our equation. So let's see a picture of what is going on. So this is for hydrogen transition. You see, this is N equals to 1. It absorbs energy. It can absorb energy until the electron leaves the atom. When this happens, we say ionization has occurred. So it can absorb enough energy. One electron in the N equals to 1 cannot absorb enough energy until it goes to N equals to infinity and leaves the atom. But it can decide not to leave. It can reach to a level where it doesn't leave. It starts falling back. When it leaves from N equals to 5 and gets to N equals to 1, this is ultraviolet light. We can't see this. It's not colored. But when it leaves from N equals to 5 to N equals to 2, it has about 434 nanometers. This is purple in color. When it leaves from N equals to 4 to N equals to 2, it is green in color. The wavelength is about 486 nanometers. And when it leaves from N equals to 3 to N equals to 2, it appears red. And the wavelength is 656 nanometers. But if it's smaller, N equals to 3, it's infrared wavelength. We can see infrared. So this is the energy transition for hydrogen. So other atoms with multi electrons have something similar like this. So let's do some calculation. Calculate the wavelength of light emitted when hydrogen electron transition from N equals to 6 to N equals to 5. N initial is N equals to 6, N final is N equals to 5. And this is our Rydberg constant. We want the wavelength. So we are going to find the energy of the electron, change in energy. Then we now find the energy of the atom. Then we find the energy of the photon and the wavelength. So these are our equations. See the equations that we're going to use. So this is to find the energy of the electron. Then we find the energy of the atom, the energy the atom absorbs. Then we use that to find the wavelength. So that's the energy of the atom. So N equals to 5 is the N final, the principal energy level which it finally got. Then this is the initial. So this is our constant. So when you do this calculation, this is the value you're going to get for the energy of the atom. Now we want to find the energy of the photon, which is equals to the energy of the atom. So energy of the photon, of course, put minus here, and that's all we did. So minus becomes positive. Then let's find the wavelength. So Planck constant times speed of light over energy gives us a wavelength of 7.46 times 10 to the 6 nanometers. So this is Planck's constant, this is speed of light, and this is the energy of the photon. So that is how we find the energy of the photon. So please, from the example of this, please, can you do this? Take your time and try and do this on your own. Calculate the wavelength of light emitted when the hydrogen electron transition from n equals to 2 to n equals to 1. To n equals to 1. So try and take some time and do that. I'll show you the answer. So that's your answer. You should get your answer should be 1.21 times 10 to the 7 meters. So make sure you do your practice. Follow the example we did in the last calculation and try and do this one. So your answer should be, let me write it here again. (1.21) times 10 to the minus 7 meters. That should be your answer. Okay. We want to talk about probability density, and we'll look at some shapes of orbitals. Probability density. We symbolize it as psi. This is psi, a function psi squared. So the probability density function represents the total probability of finding an electron in a particular point in space. So the probability density function represents the total probability of finding an electron at a particular point in space. So for S orbital, when you calculate the probability density, S orbitals are spherical. See them? It's spherical. And if we want to put it in the form of psi function, it looks like this. It means as the radius increases, the probability density decreases. So the further you go away from the nucleus, that's what this is showing, the probability density decreases. The probability of finding an electron far away from the nucleus decreases. So the shape of S orbitals are spherical. Shape of orbitals. The angular momentum quantum number L determines the shape of orbitals. For a particular energy level n, L can have integer values from 0 to n minus 1. We've talked about this. So each value of S is called by a particular letter that designates the shape of the orbitals. So L equals to 0, S, it designates the shape. L equals to 1 is P, designate the shape. L equals to 2 is D, designate the shape. As we said earlier, we talked about it. Now you're going to see them. So let's look at how S orbitals look like. So as we said, S orbitals are spherical in shape. Each principal energy level state has one S orbital, and all of them are spherical in shape. The lowest energy orbitals in the principal energy level, yes, this is the lowest energy orbital in the principal energy level states, is the lowest. It has the lowest energy. Then it is spherical, and it has nodes where you will not find electron. So number of nodes is n minus 1. So as you go higher, you have some area in the s orbitals that you will not see electrons. We call that nodes. So this is s equals to 2. It has L equals to, this is 2s. Is n in n is 2, n equals to 0. You see, it has just one node. It has one node. For s equals to 3, 3s orbital, the n is 3 and the L is 0. It has two nodes, you see. That's the node where you will not find electron. So, you see, look at the shape of this one. The total radical probability. That's how I look. You see that node? You see. And for this one, you have two nodes. That's areas you will not find electron. Let's look at p orbitals. P orbitals L equals to 1. The principal energy state above n equals to 1 has 3p orbitals. Yes, the principal energy level state above n equals to 1. N equals to 1 does not have p orbitals. But n equals to 2 has p orbitals, and there are 3 of them. The ml is minus 1, 0, and plus 1. Each of the 3 orbitals points along a different axis, px, py, and pz, but they are the same. The second lowest energy orbital in a principal energy state, that's the second energy level orbital, looks like a dumbbell. That's their shape, you see. Px is on the x-axis. This is x-axis. You see them here. And looks like this. Py is in the y-axis. You see, it looks like this. And Pz in the z-axis looks like this. The radial distribution function. That's how it looks like. Then let's look at the d orbitals. L equals to 2, d orbitals. Each principal quantum state above n equals to 2 has 5 d orbitals. Minus 2, minus 1, 0, plus 1, and plus 2. 4 of the 5 orbitals are aligned in a different plane. The field is aligned with z-axis, dz squared. So we have dz squared, dxy, dyz, dxz, dx squared, dash dy squared. It is the third lowest energy orbitals in the principal energy state. So these are the shapes of the orbitals. You see, we have this clover shape. We have this clover shape. And let's look at L equals to 3f orbitals. Each principal energy state above n equals to 3 has 7 d orbitals. Minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. It is the fourth lowest energy orbitals in the principal quantum energy state. Mainly 8 lobes. So I want to thank you again. We have come to the end of chapter 7. Please don't forget to do the question, the odd number question practice. You see that in appendix 3. Thank you so much. See you next class.